action of minimizing hypersurface. Okay, let's restart it. Our third speaker is Shihang He. He is a PhD candidate in Peking University. His talk title is Foliation of Area Minimizing Hypersurface in Asymptotic Flat Manifolds and Schoen's Conjecture. Okay, so Shihang, okay, you can get started.
Okay. Thank you so much. And today I will talk about something about the area minimizing hypersurfaces in asymptotically flat manifolds and Schoen's conjecture. And this talk is based on the joint work with Yuguang and Haobin Yu. And this is the content for today's talk. In the first part, I will introduce the construction of foliation of area minimizing hypersurfaces in asymptotically flat manifolds of dimension greater than or equal to 4. And for simplicity, we just use AF to denote asymptotically flat. And in the second part, I will say something about that is more closely related to the positive mass theorem. We study the behavior, the free boundary minimal hypersurfaces in AF manifolds. So let's begin with the first part. That's about the foliation of minimal surfaces in AF manifolds. And let us start with some well-known definitions. We say a minimal hypersurface is stable if its second variation is non-negative. And we say a minimal hypersurface is area minimizing if it has least area under compact perturbation. And from the definition, you can see that stable is a local assumption and area minimizing is a global assumption. And area minimizing will imply stable. So one of the most important application of the minimal surface theory was due to Shihang He in their resolution of the positive mass theorem and their resolution of the general conjecture that the N-torus emits no positive scalar curvature metric by introducing a dimension reduction principle by minimal hypersurfaces. Then just after Shihang He's work, Fischer and Shing has systematically studied stable minimal surfaces in three manifolds with a negative scalar curvature, and they obtain this classification result. They have shown that if this stable minimal surface sigma is compact, then it can only be the S2 or is the totally geodesic torus. And if sigma is non-compact, then it is must be a plane or a totally geodesic cylinder. And subsequently, there are many also studying the rigidity aspect in the Fischer-Kobayashi theorem. Actually, in this theorem, they always consider a stronger assumption that when sigma is an area minimizing, and they deduce the global rigidity for the ambient space. Actually, Tsai and Galloway have shown that if a three manifold with a non-negative scalar curvature contains an area minimizing torus, then the ambient space must split as the standard torus or torus times R. And the non-compact case, when sigma is an area minimizing cylinder, Chodosh, Edmeyer, and Moreau also obtain a ambient space rigidity. For the case when sigma is S2, you could not expect in general that the ambient space has rigidity, but Bray, Marcos, and Nervis can also prove a system rigidity result in this case. That is, when sigma attains an extreme area, then you can say something about the rigidity of the ambient space. So these three cases constitute three of the four the Fischer-Kobayashi theorem, and the remaining case is that when sigma is a plane, and that corresponds to a version of Schoen's conjecture. Actually, there are many different versions of Schoen's conjecture, like Professor Wang has talked in the last talk, another version of Shihang's conjecture about a singular metric and a positive scalar curvature. And here, this Shihang's conjecture is another one which says that if M is a three-dimensional asymptotically flat manifold with a negative scalar curvature, and it contains a non-compact area minimizing boundary, then M must be isometric to the standard R3. And this version of Shihang's conjecture was resoluted by Carlotto, Chodosh, and Edgemere in 2016. They have shown that this conjecture is true in dimension 3. So this shows in dimension 3, actually, if you assume the negative scalar curvature in the AF manifold, then the existence of a area minimizing hypersurface gives strong rigidity of the ambient space. So in light of this result, it is natural to ask whether similar thing holds in higher dimensions. That is to say, if a higher dimensional AF manifold with non-negative scalar curvature contains an area minimizing boundary, is it necessarily isometric to the standard one? However, in general, this may be false due to a very early observation by Xing Yao in their article on peanuts. They have observed that in dimension n between 4 and 7, for any AF manifold, there always exists a non-compact area minimizing hypersurface. So this means in higher dimension, you can not expect this kind of so strong rigidity, since you can construct an area minimizing hypersurface in an arbitrary ambient space. A similar phenomena have also been observed by Edgemere and Kober. They have shown that when the ambient space is a standard Schwarzschild half space, then you can construct infinitely many area minimizing hypersurfaces, and which further form a smooth foliation. So today, our first main result will be closely related to Xing Yao and Edgemere Kober's observation, which will be carried out in the most general setting. And before we introduce it, let us begin with some notation. Here, M always denotes AF manifold, and outside a compact set, you can associate it with a coordinate system, and we use the Z coordinate to represent the last coordinate. It is in the vertical direction. That means the height direction. Then we use ST to denote the hyperplane Z equal T. So that is a hyperplane in the AF manifold in the horizontal direction. And we use CR to denote a cylinder of radius R. This cylinder is a vertical cylinder and has radius R, which is perpendicular to the hyperplane ST. And lastly, we say a complete non-compact area minimizing hypersurface is asymptotic to some hyperplane ST if it can be written as a graph outside some compact set. And we have that the graph function tends to 0 when x tends to the infinity. So a theorem due to Edgemere and Kober shows that for a general non-compact stable minimal hypersurface in an AF manifold, it has very nice description in the infinity. Actually, you can always show that this surface is asymptotic to some hyperplane. Yeah, so this shows that area minimizing hypersurface in AF manifolds has very nice behavior in general at the infinity. Now let me introduce our first main result, that is stated for an AF manifold of dimension n between 4 and 7 with the asymptotic order assumption. Then we're able to show that the existence of an area minimizing hypersurface sigma t that is asymptotic to a hyperplane ST. Yeah, that means it can be represented by a graph with graph function ut over the hyperplane ST. And we also have a decay estimate for the graph function ut. It tends to zero very fast when the point goes to the infinity. And furthermore, when t is sufficiently large, that means when the hyperplane is very high or very low in the AF manifold, you can show that the area minimizing hypersurface asymptotic to that hyperplane must be unique. Actually, you can expect that the hypersurface has a very nice behavior since the geometry of the AF manifold at a very far place is very close to that of a standard Euclidean space. Yeah, so it's why you can expect this uniqueness result. And lastly, we are able to show that for this large T, the area minimizing hypersurfaces sigma T constructed above actually form a smooth foliation. That is in the region when T is sufficiently positive or sufficiently negative. And here is a picture for this foliation, which are constructed when T is large or small. However, when T is not so large, there may exist points such that the area minimizing hypersurface asymptotic to that hyperplane is not unique. However, you can show that such kind of point only exist in the closed interval, and there are at most countably many such kind of points. So any question about the statement of this theorem?
So I don't understand, your explanation in counterpoint, and then you draw a picture. What do you tell us?
Yeah, here is an ideal case that it has only 2 points that the corresponding at the corresponding level, the area minimizing hypersurfaces is not unique. But in general, you can show that there exists at most countably many points that accumulate in a closed interval. Yeah.
Oh, you
And
can
out
explain
of yeah.
Okay.
Okay. So I think this is not important because actually the point is that you have only need to focus when T is very large and very small. Yeah, in this region, the behavior of the area minimizing hypersurface is very nice. They form a smooth foliation.
Okay, so before you mention your main theorem, you talk about the Ekman and the Koba, their result. Did you use there, or you remove something and improve it?
Yeah, actually, so their result is more. I think it says something for general stable minimal hypersurface in the AF manifold, and our result just maybe a description in another viewpoint.
Okay, and you can continue. Okay.
Yeah, because this is a construction result. Yeah, actually, the point is to construct infinitely many such kind of area minimizing hypersurfaces, and their result is a description for a general stable minimal surface.
Oh yeah. Oh, I got it. I got you.
Yeah. Okay, thank you. So let us just go ahead. Yeah, there are several remarks. The first is that, as you can see from the theorem or the observation by Xing Yao, that the case of dimension 3 and higher dimensions are tremendously different, since in dimension 3 you have Xing's conjecture, and in higher dimensions you can construct it so many area minimizing hypersurfaces. And another point I would like to explain is that the foliation actually gives an intrinsic description of the AF manifold. It shows that the AF manifold is absolutely composed of area minimizing hypersurfaces, except finitely many such kind of shielded region. The remaining parts are composed of minimal surfaces. And another application is that the foliation can be used to detect the mass when the metric is very close to the Schwarzschild one. When the mass is positive, you can think of the foliation to behave like this, and the negative, and when the mass is negative, you think the foliation to behave like the right-hand side picture. Because you may think of the standard Schwarzschild metric. If the metric is Schwarzschild, then that is relatively small outside, and the metric is larger inside. So if you want it to have less area, the foliation may be convex, and the same thing holds for the negative mass case. And another point is that from the foliation structure, you can see that the modular space structure of area minimizing hypersurfaces in a higher dimensional AF manifold is well understood outside a compact set. You can show that if we use M to denote the modular space of minimal area minimizing hypersurfaces in MG, then this modular space must be diffeomorphic to Sn-1 times the half line. Here, the Sn-1 factor comes from the freedom of the choice of the asymptotic of the hyperplane, that your foliation is asymptotic to, and the half line comes from the parameter of the foliation. So this shows when the minimal surface is sufficiently far, then the structure of the modular space of it is even well understood. And lastly, I would like to mention actually, it may be interesting to compare this foliation with the foliation, CMC foliation constructed by Schoen and Yao. However, at the present step, we do not know if there is some necessary connection. There are some, the difference is that in our case, the leaf of the foliation is a hyperplane, and in the Schoen-Yao's case, their leaf is a CMC sphere. So these are some remarks about the main theorem. And next, I would like to say, although the main result was proved assuming a dimension restriction that between 4 and 7 before, due to the restriction of the regularity theory for minimal hypersurfaces, it can also be extended to higher dimensions if you allow the minimal surface to possess singularity. Actually, the existence result may be absolutely the same if you allow the sigma t to have singularity. However, you can actually show that this sigma t is smooth outside a fixed compact set. It means that singularity can appear only in a fixed compact set, regardless of t. This is because the area minimizing hypersurface always have a very nice density estimate at the infinity, so you can expect such kind of regularity result due to Alice type theorem. So as a corollary, you can actually show that the foliation structure still exists because when T is sufficiently large, then the whole minimal surface sigma T is smooth, and they also form a smooth foliation. Yeah, so when you use the minimal surface to consider the positive mass theorem in higher dimension, you may meet the difficulty posed by singularity. Because in general, when you construct the minimal surface, it always has singularity. However, you can still show that there are infinitely many smooth area minimizing hypersurfaces in higher dimensional AF manifolds, but we do not know whether these surfaces can be used to prove positive mass theorem in higher dimensions. Lastly, let me just give some comments on the existence. Why does the hypersurface sigma T exist when the dimension of n is greater than or equal to 4? And this is because of a C0 estimate lemma, which we let sigma TR to be the Plateau problem with boundary that is the intersection of the hyperplane of height T and the cylinder of radius R, and we aim to show a C0 estimate for this graph, for the graph function of sigma TR. This is not true in dimension 3 as it contradicts with Schoen's conjecture. And the proof is by using a catenoidal barrier devised by Xingyao in 1981. This barrier is just like a catenoid as depicted by this dotted line. And we want to show that the hypersurface lies below the catenoidal barrier. And you can prove by contradiction. If it is not the case, then you just move the catenoidal barrier upward, and at some time it will touch the hypersurface. However, Xingyao has computed that the mean curvature of the catenoidal barrier is positive, and in this computation, they have to use the dimensional restriction. That means in dimension 3, you cannot obtain the sign of mean curvature here. So you will use the maximum principle to obtain a contradiction, so that will show that sigma RT is lies below the catenoidal barrier and proves the existence. And that is about all about the foliation result. Is there any questions about the first part?
So this means you solve the free boundary minimal surface, and then this minimal surface will stay in some compact set, uniformly compact set. That's
yes, its z coordinate is uniformly bounded. As it means it must lie between two parallel hyperplane.
oh, okay, I got it.
Yeah, and here we solve a Plateau
But this
problem.
is not correct in 2 dimension, in 3 dimension.
Yeah. Not correct in 3 dimension because the computation of the sign of this mean curvature have to make essential use of the condition that n is greater than or equal to 4.
Okay, I got
it. Yeah. And maybe another viewpoint is comes from the fundamental solution of Green's function, since when dimension is 3, then the surface has dimension 2, and at this time the Green's function behaves like a norm, and in higher dimensions the Green's function decays to 0. Maybe this is another understanding. Yeah.
okay, I got it. Okay.
Yeah, so this is all about the foliation result, and in the remaining part, let me give, just to present some application. that concerns the behavior of free boundary minimal hypersurfaces in AF manifolds. And this part is closely related to the positive mass theorem, and we will assume the negative scalar curvature condition for the AF manifold. This is different with part one, since in part one there is no curvature condition for the AF manifold, and that's about the construction result that could be applied to general AF manifolds. So in light of Shin's conjecture in dimension 3, we may naturally pose the question, to what extent can Shin-type conjecture hold in higher dimensions? Of course, you cannot expect this in general, since here I just mean Shin-type conjecture to be something, if you have an area minimizing hypersurface and you assume the ambient space to have the negative scalar curvature, then you get some rigidity for the ambient space. So this cannot be true if you pose no additional condition because of the result just mentioned above. So in order to get a comprehension of this theorem, it may be the first step may be to understand the rigidity for a single hypersurface, and only when you have understood the rigidity for hypersurface, you can say some more thing about the rigidity of the ambient space. And this is related to the infinitesimal rigidity result. And here we have to introduce a notion called the strong stability. We say a stable minimal hypersurface to be strongly stable if it has the negative second variation that applies to the test function, which equals to a constant outside a compact set. So this, of course, strongly stable is something stronger than just stable, because in the definition of stable, you just assume phi to be a compactly supported function. So this strongly stable notion was first devised by Shihang in his proof of the positive mass theorem of dimension no greater than 7 by devising a non-compact dimension reduction strategy. And the infinitesimal rigidity result by Carlotto, Edgemeyer, and Kober is that if the AF manifold has the negative scalar curvature and sigma is strongly stable, then sigma must be flat, totally geodesic, and normal-racing curvature vanishing. So this means strongly stable can give a rigidity for the hypersurface combined with the negative scalar curvature. And in dimension 3, a very special point is that when sigma is stable, then it is automatically strongly stable. So this is why in dimension 3, this is one of the reasons why in dimension 3, the rigidity can be so strong. You can freely obtain a rigidity for the stable minimal surface. Yeah, because it is automatically strongly stable, and you apply this infinitesimal rigidity result. So in light of this infinitesimal rigidity result, it is natural to ask whether if you assume the existence of a strongly stable minimal surface, it could be enough to deduce Shin-type conjecture in higher dimensions. However, this is false by a counterexample due to Edgemeyer and Kober. They have shown there exists a non-flat AF manifold with a non-negative scalar curvature that equals to the Euclidean metric in the lower half space. And in the upper half space, it is non-flat. So in the lower half space, each horizontal slice will be the standard Rn-1, and that would be a strongly stable hypersurface. So the example by Edgemere and Kober illustrates that if you do not impose certain global condition, then you can never deduce a rigidity for the ambient space, because here you need some global condition, and here strongly stable is just a local condition. And there are several results. Carlotto have shown that Schoen's conjecture is true for a asymptotically Schwarzschild manifold that contains a strongly stable sigma, and Edgemere-Kober have proved Schoen's conjecture for AF manifold that contains a hypersurface, which is the limit of isoperimetric hypersurface. So the theorem by Edgemere and Kober illustrates some global assumption of the hypersurface. It's the limit of a sequence of isoperimetric hypersurfaces. And next is our second result. Here we assume M is also an F manifold with non-negative scalar curvature. And the dimension is between 4 and 8. And I may just give some remark of the dimension 8 at the last of this talk. And here we assume sigma R to be a free boundary minimal hypersurface that minimizes the volume of the vertical cylinder of radius R. So this kind of sigma R may not exist, or it exists and you can obtain a sequence of such kind of minimal hypersurface. Then one of the following must happen. The first is corresponds to the rigidity case, that is when the mass is 0 and M is isometric to the standard Euclidean space. And the second case and the third case corresponds to the positive mass case. And the second item says that there exists for sufficiently large R, such kind of free boundary minimizing hypersurface in the large cylinder does not exist. And the remaining possibility is that you have for any sequence of R that tends to infinity, the free boundary minimal hypersurface must drift off to the infinity. And here is a picture for this theorem that is to say when the mass of the AF manifold is positive, then any sequence of solution of the free boundary minimal hypersurface must drift off to the infinity. It cannot intersect with a fixed compact set. Actually, this gives a certain global effect of the positive mass. This says that the condition of positive mass will have some geometric consequence in general. So the positive mass will push this sequence of free boundary minimal hypersurfaces to the infinity. And we would like to say that this theorem is actually, it consists of two parts. The first part is the positive mass theorem, and the second part is the global effect of positive mass as shown above. Indeed, you can deduce the positive mass theorem from theorem B, since if the positive mass theorem does not hold, then you have a negative mass, and you have a two standard hyperplane barrier that forces the solution of the free boundary minimal hypersurface to accumulate. And this will violate the theorem, since this theorem has already claimed that any sequence of this kind of free boundary minimal hypersurface can never accumulate unless it is the critical case when the mass is 0. Yeah, and the second part is just mentioned above. It's the global effect to the positive mass. It pushes the free boundary minimal hypersurface to the infinity. And with this theory, you can also obtain a version of Schoen's conjecture. You can introduce the notion of globally minimizing. That means a hypersurface, if we say a hypersurface is globally minimizing, then the intersection of it with a cylinder has the least area among all other hypersurfaces in the same cylinder. So as a corollary, we can see that if an AF manifold with non-negative scalar curvature contains a globally area minimizing boundary, then the ambient space is actually flat, which may also be regarded as a version of higher dimensional Schoen's conjecture. And here is just a picture of the proof. We will adopt a metric perturbation argument initiated by Gang Liu in the three-dimensional mirror conjecture to construct a sequence of new minimal hypersurface that is also strongly stable. And we will show that this newly constructed hypersurface coincide with the leaf of the foliation constructed in the first part. And this will show that when T is very large, then each leaf of the foliation is strongly stable and which has a local rigidity. And so you can show all the foliation has rigidity, which will conclude the proof of the theory. And any question about the second theorem? Okay, so let us just go ahead and finally, I would like to just say a little bit word in the dimension 8 case. Actually, in the dimension 8 case, the only difference is that there is no infinitesimal rigidity result that you can apply. So we have established an infinitesimal rigidity result for strongly stable minimal hypersurfaces with isolated singularity. You assume M is an A-dimensional AF manifold with non-negative scalar curvature, and that contains a strongly stable minimal hypersurface with isolated singularity. A priori, we just we allow the existence of the singularity. However, you will conclude that there actually exists no singularity, and sigma is smooth and is isometric to R7 which is totally geodesic with the normal Ricci curvature vanishing. So this theorem can also be used to obtain a proof of the positive mass theorem in dimension 8. In general, the philosophy may be you expect a suitable version of the singular positive mass theorem in dimension n is enough to guarantee a positive mass theorem in dimension n plus 1. So in this theorem, we can see that singularity actually have some positive effect since it excludes the existence of singularity. If that means if you have singularity, then you know that the second fundamental form is very large around that singularity, and this will contribute to a large term of the scalar curvature for the hypersurface due to the second variation formula. This will show that the scalar curvature for the hypersurface is very large in spectral sense if the singularity set is not empty. So this infinitesimal rigidity follows from a singular version of the positive mass theorem in spectral sense, in strong sense. Here we say this spectral condition hold in strong sense if you allow the test function to be a constant outside a compact set that goes aligned with the definition of strong stability. And in the last screen, I would just like to say a crucial step of the proof of this infinite symbol rigidity result is a positive mass theorem with arbitrary end under the assumption of spectral scalar curvature non-negative. And this strategy have also been adopted by Schoen and Wang, as just mentioned by Professor Changliang Wang in the last talk. In their work, they proved a positive mass theorem with conical singularities, and their strategy is to conduct a blow-up argument and apply the positive mass theorem with arbitrary ends. Here we just adopt a similar kind of strategy and reduce this spectral positive mass theorem to a version of the positive mass theorem with arbitrary and under the spectral scalar curvature non-negative condition. And I think that is all the content of my talk. So thank you very much.
So any questions? Okay, so can you go back your, sort of type of generalization of the Schoen's conjecture, right? So you say you have some globally area minimize, yeah, and
this page.
yeah, I know. After this, so actually, in my mind, I haven't worked on this for many years. So, can you explain a little bit more about the three cases, or, because this time you say the mass is on any compact place, right? The mass is accumulated in compact region, right? In
Oh
my
yeah,
mind,
yeah.
I always think about that infinity. Can you
Oh
just
yeah.
briefly explain why that kind of three case? I think you explained, but I don't understand. I didn't understand it.
Yeah. Here I just want to want to say that when the mass is negative, then the solution of the free boundary minimal hypersurface can accumulate. Since if you assume M to be asymptotically Schwarzschild, then you know there exists two hyperplane. Maybe here a hyperplane and here a hyperplane. And due to the negative mass condition, these two hyperplane are mean convex with respect to the outer normal. So they will
Yeah.
serve as a barrier. And when you solve for the solution, the free boundary minimal hypersurface, you can guarantee that they lie between this hyperplane and they will intersect with the fixed compact interval.
Okay. You mean if the mass is negative, you can have two hyperplane as the barriers,
Yeah,
and then you play the game. And
yeah.
okay, but if it's positive, you cannot find two being convex hyperplay and play the game. That's what you want to say?
Mm. Yes, actually, in positive, you can when you do computation, the positive to the mean curvature to any hyperplane is negative, so you cannot find this barrier. So the result is that the solution to
Oh,
free boundary minimal hypersurface must drift to the infinity.
the essential part is because the mass need the mean convex hyperplay, and then maximum principle works, and then you can say what you want to say, right?
Yes, theoretically, you can think in that way.
Oh, okay. Oh, yeah, I got. Yeah, and you have this contains a global area minimizing boundary and it's flat. Okay. Yeah, I got you. Okay. So any questions from other audience? Okay, so since there is no other questions, let's end this talk. Okay, let's thank Shihang again.